Now we will learn Castigliano's theorem about the slope and deflection of a beam, of a loaded beam, of course. So the statement of Castigliano's theorem says if a structure is subjected to a number of external loads or couples, the partial derivative of the total strain energy with respect to any load or couple provides the deflection in the direction of that load or couple. Okay, I am simplifying it. I am just showing you the mathematical form. Suppose there is a beam which is simply supported and it is supporting some other number of loads. Okay, suppose this one is W1, this one is W2, this one is W3. Okay, and because of that the beam takes a shape like this, and this is say x1 and this much say x2, this deflection say x3. So for W1 load the deflection is x1, for W2 load deflection is x2, and for W3 deflection is x3, and so on. Okay, so if that happens, we can find out the total strain energy U, just like in our earlier lecture we did. So U can be found out. Now if U can be found out, then the partial derivative of U with respect to a particular load will give you the amount of deflection. Okay, so this partial derivative with respect to the other load will give you that corresponding deflection. If you want to find out x3, then x3 can be found out by partial derivative of the total strain energy with respect to the position the load acting is W3. Now we know that U is equal to 0 to L m squared dx by 2 EI, where EI is flexural rigidity, and for any beam, for homogeneous material E is constant and I is also constant for symmetrical beam. Now we have known that the deflection delta I, where I can be 1, 2, 3, 4, 5, n, anything. So del U, del Wi. Okay, so deflection at ith point will be equal to partial derivative of total strain energy with respect to the load at ith point. Okay, so if it is so, then we can write it as 0 to L m square. Okay, so 2m into del m del Wi, and below it 2EI dx. Okay, so it actually becomes 1 by EI integration 0 to L m into del Wi dx. Now we can find out the expression of m, and we can find out del m del Wi, and then we go on with the equation. Okay, and this will give you the deflection at that particular point because of the bending moment. Okay, now if at any particular point, please focus here, if any particular point there is no load, so at ith point there is no Wi, then you have to assume a point load there, and later on before integration you have to put it to 0. Similarly, when you want to find out the slope, then you have to put that assumed virtual couple to 0. How we will do that? We know if a beam is loaded and at any point there is no particular couple, but you need to find out the slope theta I, then how can you find it out? Del u del mi, where mi is the virtual couple. Now if at any point at a particular value of I, if there is no couple, then you have to assume there is a virtual couple, and later on before integration we will put it to 0. So it will become 0 to L m by ei del m del mi into dx. So it will give you 1 by ei into 0 to L m into del m del mi dx. So you can understand that m is a function of mi. Okay, and we will solve a problem for better understanding. We will solve a problem here. Suppose there is a cantilever which is having a uniformly distributed load throughout the beam, and the loading rate is small w, and this total length is small l. Okay, so we have to find out the deflection and the slope at the free end. That is our job. Okay, now if we take any section at a distance of x from free end B, then we have to understand that we cannot find wi here, okay, because at B there is no load. At B the loading value is 0, so that's why we will assume there is a virtual load. Okay, there is a virtual load which is say capital W, is virtual load. So the bending moment at section XX at a distance x from B will be equal to minus wx minus w into x square by 2. So its derivative with respect to w will give you del m del w will give you minus x. Now by Castigliano's theorem, the value of delta B will be equal to 0 to L m by ei into del m del w dx, just this formula. So here we will put this w equal to 0 here before we put it here. Okay, so the m value, this m value to be written, please focus what happening. There is no load at w, so we have imagined there is a w, but when you find out this mx and before putting the value in integration, we will consider this w as 0. Okay, So the m value is only wx square by 2 divided by ei, and del m del w is only minus x, okay, into dx. So this is we have got. Now by calculation, putting the values, we will get WL by 4 divided by 8 EI. Okay, so this is the value of the deflection at end B. So what happened here? We have assumed that there is a point load which is having a value of capital W, and we have found out the moment at a distance x from B. We have found out the bending moment because of this portion. So we have found out this expression, and we have found out del m del W, and we have found out this minus x. Now when we put the m value here, we put this W equal to 0, as there is no physical load. So that's why we put capital W equal to 0, and this only remains, and this value is placed here. Okay, so this is how we have found out WL by 4 into 8 EI. Okay, now our job is to find slope at the free end. So for this purpose, we will imagine, let's redraw this. This is A, this is B, this is L. To find out the slope, we need to apply a dummy clockwise couple, which value is MB. Okay, we have applied a dummy clockwise couple MB at B, because we need to find out slope at point B. That's why we are applying the virtual couple MB at point B. Okay, so then bending moment, in this case the bending moment at a distance x, MB, bending moment at a distance x, just like the previous problem, bending moment at a distance x from B. Okay, the bending moment will be minus MB minus W x square by 2. Okay, and del MB will be equal to minus 1. Okay, so we have these values. Now we will write the equation, which we know that theta B has equation 0 to L m by EI into del MB to dx. Okay, where m is a function of MB, that we have known already. So if we put the values, before we put m here, we will place MB is equal to 0. So here this MB we have to assume to be 0, because there is no actual couple. We have assumed a couple, so the value should be taken 0. So this m we will only take this much. So for this, in this formula, this m will be equal to only minus wx square by 2. This is minus. Okay, and this integration from 0 to L by flexuality dt EI into this del m B. Here we have found out is minus 1 here. Okay, so we will place the value here as dx. So this is the loading. Sorry. Zero to L x square dx, and that will give you WL cube by 6EI. So this is the slope at point B. Okay, this is how you need to use the Castigliano's theorem. Okay, we will solve another example by Castigliano's theorem. Let us have the previous chapter's problem. The energy method. In energy method we have used that same problem that we will solve here by this method also, by Castigliano's theorem. This was A, this is B, this is C, there is W point load, and this distance is A, this distance is B, this is L. Okay, so the reaction, just like in previous problem, will be this, and the reaction here will be this. Okay, we have done that already. So bending moment at a distance x from A will be equal to mx, and that let us consider m. So W into B by L into x, and it will be positive. So at a distance x from A, bending moment m will be WB by L into x, reaction into x. Okay, now so if we do del M del W, then we will get Bx by L, which is very simple. Now similarly, this is for section A to C. Now if we do this for section BC, what happens? M is equal to WA by L into x. We will consider bending moment at a distance x from B. Okay, so it becomes M equal to WA by L into x, reaction into x. Okay, and del M del W becomes x by L. Okay, now by Castigliano's theorem, okay, this deflection